Dear friends, welcome to my channel AMP Workshop at the rate of Power System, Workshop 1 Power System Protection. Under this Power System Protection, Session 1, we have already completed last week, where we have discussed about the requirement of protection system for a power system. We have also discussed about the basic components or devices required for a protection system, as well as the various parameters which are required to measure the performance of a protection system. Now, today's session 2, we will be discussing today's session the transition of electromagnetic relay to solid state relay to the digital numerical relay. Electromagnetic relay we consider as a first generation relay, then this solid state relay we consider as a second generation relay, and digital or numerical relay we consider as a third generation relay. Now, when we look into the transition of these relays, this is started from 1960 onward, but we'll go to these details gradually. Now, before going into the details, I would just like to highlight my details. My name is Anand Paul. I am a retired electrical engineer after serving 35 years. And out of 35 years, I have the opportunity to work with multinational consultant, major EPC contractor, and for the last more than 2 decades, I have been working with one of the leaders of oil producing and processing company in Abu Dhabi. Now, when you go to this today's session 2, in this session, we will be discussing about the transition of the first generation relay to second generation relay to third generation relay. Then after that, we will discuss about the each type of relay, what is the architecture, what is the working principle, then what are the basic characteristics of those relay, and then relative merits, demerits also we will discuss. Now this session, we have received a comment from various subscribers and sharing those who have gone through this my presentation. I must appreciate their efforts and welcome them to again. And at the same time, I would like to thanks for going through this, and I have checked already their comments, and based on the comments, most of the viewers, they have said that to reduce the timing, accordingly I have planned to make this session within 45 minutes. If within 45 minutes the session is not getting completed, then I will be splitting into 2 parts, part 1 and part 2. So let's start session 2, which is transition of the first generation electromagnetic relay to second generation solid state relay to third generation digital or numerical relay. Now, if we look into this up to 1960, we see from the invention of electricity, all the power system or power company or utility company, they are using electromagnetic relay, and that was predominantly, or it was dominating the market up to 1960. Now, with from the 1930 onward, there is this development of the semiconductor electronics, and with the tremendous development of the semiconductor electronics, there is a lot of electronic devices came into the market. That is the diode, transistors, FET, MOSFET, TRIAC, all these electronics component, and they are already established in the market, in the industrial or the end user started using these components. So by 1960, these all scientists, researchers, they thought that to use these components to make a relay or the switching device relay, so that this presently electromagnetic bulky relay could be replaced by solid state devices. So they started working. By 1965, they come out with a miniature version of these relays, and they started using this relay and they performing well. So with this achievement, then the scientists, researchers, all these technologists, they are planning to use this further development of this relay to use in the power circuit. So by 1965 to 1975, there is a tremendous development, and by 1970, people started using this, individuals started using this solid state relay for the power circuits. So from 1970 to 75 to 1985 up to 90, this solid state relay was tremendously used in the market, and it gradually replacing this application of electromagnetic relay. After 95, after 90, but by the time of 85, there is a digital technology comes into the picture, and there is a microprocessor was developed, and the from 1985 onward, microprocessor were being used for the various minor control like a DC motor control, for metering purpose, then a small control application, process application, microprocessor was using. So when this microprocessor with suited algorithm and the interface, from 1985, there is a new version of the relays comes into the picture, that is called digital numerical relay, where microprocessor was the main components with the various interface, input-output interface, and the algorithm. And from 90 onward, this relay was in the market, and people started using this relay, bypassing this solid state relay. So if we see the market from 1990 or 95 onward till today, the market is dominating by the digital or numerical relay, which has a various advantage over the other versions of the relay that we'll discuss separately. So if we see the transition of the relay, we can say up to 1960, all the end users, they are using electromagnetic relay. From 1960 to 1965 up to 70, this solid state relay was in use, but in the small power application like a printing machine, a small self-starting purpose of a motor, then lift, packaging unit, all this purpose. But from 1970 onward, this relay came into the market for using the power circuit, and it was dominating up to 85. From 85 to 95, there is a transition period where this 85 end, this digital relay, when they came into the picture, then from 90 onward, this solid state relay used become GIST, and from 90 onward, people are using digital numerical relay. So we can say from 90 to till today, digital numerical relay is dominating the market. This is the transition of the various types of relay. Now, before going further details, we need to discuss what is this relay before going to individual type of relay and their architecture, their working principle, their advantage, disadvantage, all this. Now, relay is a small control device which is getting activated by a small power supply, and on activation, it is giving some command or output contact which can control a power circuit. And that power circuit means it can open or close the breaker, or it can use for multiple control of multiple circuit by single device. It can able to control multiple devices. So let us explain. I am explaining this relay with a small electromagnetic version. This is a small relay circuit we have drawn over here. This is the relay. This is a electromagnetic relay. Basically, electromagnetic relay working on the principle of electromagnetic attraction or induction. Here, this is a solenoid and connected with an armature. Now, when this solenoid energized, immediately there is a magnetic field produced along this perpendicular to the direction of current. Then this magnetic field will, there is this armature, magnetic material, it will pull downward, then immediately this contact will make. And then this is a main power source, and then this power will go through this device. So if this is another solenoid, then if this solenoid, suppose this is a big solenoid, bigger size, if this solenoid is there, then this solenoid will be energized. It can pull another plunger, and then that plunger can control another circuit which has a huge power circuit. How is that circuit? Suppose this is a 6.6 kV switchboard. There is a circuit breaker is going to transformer. Suppose this circuit breaker, if we see there in the circuit breaker, there is a contact assembly lying inside a bottle, or it would be another extinguishing chamber. Inside this chamber, if you see, there is this is a arc extinguisher, this is a contact chamber. So in the contact chamber, suppose this is a connection is over here, power connection is over here. So this is a suit. Now here is a plunger is there. Suppose this is a plunger, and then this current is coming from this and it is going out. This plunger is here. So this is a contact position make, and then current will come out. Now if this plunger is pulled by a solenoid, then what will happen when this solenoid activated? Immediately the plunger will come out, this contact will open. So no current will flow through this. So this is a way we can use this contact. This contact, when you go to the big solenoid, suppose this is the solenoid is here, then when this solenoid energized, immediately this contact will, this plunger will come out and then circuit will open. So then that is we have shown over here. So this way, this small relay contact which is over here, that is energizing big coil, and this coil, this coil can open the breaker when it is in abnormal condition or whatever the condition. So this way, the small control device is using to open a big power circuit device, use current in a high voltage or low voltage circuit. So there, this is a schematic diagram. Now I have drawn a physical diagram how this relay works. So this relay coil which I have shown over here, this is the relay coil. That relay coil I have shown over a core. This is a yoke, and over that the coil is wound. And this coil has a supply voltage from here, and it is coming over. This is suppose DC current. So this is a yoke. So when this current pass through the coil, immediately this coil means this coil, then immediately it will produce a magnetic field. And this is a magnetic material, it is called armature, and it is mounted on a pivot, and then this is a contact point. Now when the current flows through this, it becomes magnetized, and then when it is magnetized, immediately it will attack the magnetic material. This is armature, is a magnetic material, it will attack this thing, so it will move this way. When it will move this way, immediately it will push. You see, these are the three levers. One is open position, closed position, and a common position. It is mounted on the same arrangement. Now when it's pulled down, immediately it will go up and it will push this one up, and then it will make the contact. That means this will be, if this is connected to a circuit, then this contact will be closed. That means this is the contact. Then the contact will close, means immediately current will flow through this. So this is a physical presentation of the one actual miniature relay. How this relay contact with the small control supply, DC current or AC current, this relay is, suppose this is a DC supply. With a small DC current, this relay coil energized, and that is moving, this contact is making, and that contact is energized, another big solenoid which can use to open the breaker coil. So this is the way this relay works. So in a brief, relay is a device, control device. What it does, it take a small control supply by which it give a output contact which can be used to open or close a breaker by using a solenoid. This is or a small motor, whatever is there. That is the purpose of the relay. Now next point we will go. Now this is the relay. So with the relay we will now go to the three different types of relay. First generation electromagnetic relay. Now electromagnetic relay is actually, it is a working on a principle of electromagnetic force, attractive force, or electromagnetic induction. In case of electromagnetic attractive force, we know that electromagnetic, when a coil or solenoid carries a current, either AC or DC current, the solenoid get magnetized. Until the current is there, it will be magnetized, like means that solenoid will be acting as a permanent magnet. And if that permanent magnet solenoid nearby, there is a plunger or there is an armature, it can, the magnetic material, it can pull or push depending on the direction of the magnetic field. And that push and pull which I show in the coil relay, so that can be used as a same purpose relay, that is called electromagnetic attraction type relay. So electromagnetic, in the electromagnetic attraction relay which I drawn before, that is when the magnetic force is there, when the coil is carrying the current, immediately this core is getting magnetized and the yoke is pulling this armature is making a contact. So this is a simple electromagnetic relay attraction type. Now this relay can be used for the same, instead of one contact, which I show only one contact. If there is a multiple contact connected to the same armature, then that will also work multiple contact. Then it will go multiple contact and it will control multiple circuits. Now this is a simple electromagnetic attraction type relay. Now there is another type of relay which is called electromagnetic disc type or induction type relay. In the case of electromagnetic induction type relay, what we do, that does not work on the DC, it works on the AC only, AC supply. In the case of AC supply, this AC supply or the control supply which are given to the relay, there is a magnetic core over which the wind is wrapped up. So I am drawing a schematic diagram of the relay. How does it work? I am just for simplicity, I am doing a Suppose there is a coil over here who is carrying the current. Now, when this current passes through this core, this is a magnetic core, then the magnetic field is produced. Suppose this is producing north pole and then this is producing south pole. Okay. Then this is a separation, this is a south, this is a north pole and this is a south pole. So what is this? This is a core and between these two core there is a gap and then there is a non-magnetic, it's a non-magnetic material, non-magnetic metal but conductive. This is a disc, rotating disc, circular disc. Now when this current passes through this will become magnetized, then suppose it is producing, suppose it is 1, it is 2 terminal. This produces a magnetic flux across the poles. The amount of flux passing through this, suppose that flux is I1. And now you see this two pole is not identical. Here the pole is a split type, it is called a split pole. So why we have made this pole? To make a magnetic flux is different phase between these two. There is a phase, we want to create a, this is AC supply, the magnetic flux is AC in nature. So this AC nature magnetic flux, we want to make is splitting in phase difference between these two. So that's why we make the pole shape different, so that the phase, the magnetic flux will be passing through this here phi2, that will be in different phase with a different magnitude of phi1. That is the intention of making this split phase. So there is a, if phi1 and phi2 two magnetic flux, these are not the same it is different magnitude as well as different phase difference. Suppose phi1 we write down equal to phi0 into sine of omega t. Then phi2 will be equals to, this is a phi1 0, suppose phi2 0 into sine of omega t plus there is a phase difference between these two theta. This will be for the phi2. So by this splitting the pole, we can make this flux are different. So there is a phase difference between this flux. When there is a phase difference, so at any instant due to the phase difference, there will be a electromotive force or electromagnetic voltage will be developed due to the phase difference. As this is a non-magnetic material, so what will happen due to the phase difference of these two flux magnitude, there will be a resultant flux which will be causing a eddy current generation in these discs. So if due to this flux phi1, suppose the eddy current generated over here is a I1 and here the current generated suppose I2. Now this I1 when it is passing through this I1 is produced by this due to this flux at this end due to pole, so in the disc. So this I1 will cause another magnetic force which will be acting with this, so it will be cross. This current and this flux will make one force on the disc, and this current I2 and this flux will make another force. So these two forces, there is a result, and as the flux magnitudes are different, current will be also different magnitude. So what will happen due to the current and flux reaction, as per Fleming left hand rule, there will be a resultant force acting on the disc, and then the disc will start moving. If it is that force is more than the restraining force of the disc is mounted on a pivot. So if this pivot there is a friction and there is a rotational torque required. If that force is more than the required frictional force and pivotal force, then the disc will start rotating and it will go to the end, and there is a contact similar arrangement like a electromagnetic attraction relay. That contact will break and then it will rotate, it will operate. Now we can make out in this diagram. Suppose this is a disc. We can make that how much force will be developed. Suppose this is a phi1 is working over here and phi2 is working downward. This both the flux working downward, phi1 and phi2. Okay. Now when this phi1, due to the phi1 there will be current over here, that current will be coming over here. This current is suppose I1, and due to phi2 there is a current in the disc, that is a I2. Now when phi1 and this phi2, if this is the direction of phi2 and this is the direction of phi1, I1, then if you put a Fleming left hand rule, okay, so the Fleming left hand rule, this is the direction of the current, and then this is a direction of the current, this is a direction of the, suppose this is here phi1, phi2, so this phi2, so there will be force over here. Suppose this force is F2 and at the point of phi1 the force is F1, and this due to this force what will happen, the disc will rotate. Now we know this force magnitude F1, this is this equal to proportional to the current I1, I2, F1 force will be generated due to current I2 into flux of phi1. and F2 force will be proportional to current of I1 into flux of phi 2. This is a cross reference. Phi 2, when this F2 force will react with I1 current, then the force will develop over here. So now this I1 and I2 we can calculate, I equals to I1 or I1 equal to what is that? Proportional to d phi dt, right? D phi dt. So that is proportional to phi, now d phi dt means d phi 1, that means it will be q10 into cos of omega t. Similarly, I2 proportional to d phi 2 by dt, that is equal to q20 into cos of, then there is another constant will be here omega, cos of omega t plus theta. Suppose this is a dash due to that constant. So this, now if you multiply this I2 into q1, I2 equal to this, then you will get F1 and F2, then F1 minus F2, if you do F2 minus F1, then you will get ultimately phi 1 dash 0 into phi 02 dash into sine of theta. This omega t will not be there in the final. If you calculate this thing with using sine A plus B formula, then it will come like this. So finally the resultant force will be peak value of the flux into sine theta, that is the phase angle between these two flux. Now if the phase angle will depend on the physical or this physical configuration of this pole, so this is, you can say, constant. Now you can change the force value by changing, if you want to change it, this will be variable with the design of this. So it can go maximum 90 degree means 1 and minimum 0 means 0, that means there will be no force. So that means if there is no phase difference between these two, then the force will be 0, theta will be 0, force will be 0, then this will not work. So to work this relay, you must need this phase difference between these two flux, means this pole should be splitted or pole should be different physical appearance, so that there will be phase shift between these two flux, then only it will work. Okay, now if this for resultant force F, now this flux is also depend on the how much peak value of the current. So we can say this is also proportional to peak value of the current I1 square into I2 square. If I1 I2 more or less same, then it will be I square into sine theta. So this peak value, this force will be depend on the peak value of the current. So if the and then if this is the peak force. Now if there is a resultant restriction or this friction force and the pivotal force is suppose K, then this, if I square sine theta minus K, when these will be equal to 0, then only the disc will start rotating. So that means at a stationary condition, I equal to root of K by sine theta. So if the theta is constant, the physical, this manufacturing pole phase is constant, then current is also constant just to start the rotation. When the current is more than this, then the disc will rotate. That means by adjusting the current value, we can able to make the disc rotating. So and when the disc rotate, then it will make the contacts. So this is the way this electromagnetic induction relay do work. So there is another different type of relays are there, but I am just explaining these two basic type of electromagnetic relay. Now we will come to the solid state relay. Now as I said, with the development of solid state component from 1960 onward, all the scientists, researchers, they started developing solid state relay. By 1965, it started using this solid state relay in the small power application. From 1970 onward up to 1985 up to 90, this solid state relay was tremendously were in use in the industry. Now if we see the solid state relay advantage is smaller in figure. And in the solid state, there is a rotating equipment part is there, but there is no rotating part. There is no metallic part. All are encapsulated. And switching operation of solid state component is faster than this switching operation of this. Then with the ambient condition and humidity, all these things, solid state relay is less sensitive to these ambient conditions. So solid state relay has a lot of advantage, which we'll discuss afterwards. Now, if we see the solid state relay architecture, this solid state relay has a 5 different component in its overall in a general. So this 5 component I can draw over here in a symbolic way. Suppose component 1, component 2, component 3 is a solid state relay. We say SSR. Component 4 and this is a component 5. Component 1 we say this is your input circuit. There is a 5 input circuit. Number 2, this circuit we call this is a isolation circuit. Isolation circuit. Number 3, we say triggering circuit. Triggering circuit. Number 4, we call output circuit or output device. And number 5, we say it is a protection circuit. We'll discuss all these things. So when all these 5 are together, then we get a solid state relay. I can draw a typical solid state relay on this here. This is a resistance, and then we have a optical diode. This is a suppose transistor. It goes to a filter circuit. Then it goes to a, suppose this is a SCR. SCR, and then it will go to SCR triggering. So this is a SCR and this is a conducting. This SCR will give the output, then go to the load, and then after the SCR there will be a filter circuit. It looks like a sometime like this. These are the typical arrangement. Now what is this input circuit? Input circuit is when you give some, suppose this is a diode, this is the input circuit, there is a reverse blocking diode over here. Now this part we call the input circuit. Input circuit, when you give a, suppose this diode, this is isolation circuit, this is the input circuit, okay, this first two device. Now this isolation device, it is actually optically isolated from the other part. There is no physical connection between these two. When the input voltage or current is given to this circuit, immediately this auto-isolated. It's called, it could be photovoltaic transistor, photovoltaic triode, but it could be anything. When this current goes through this is a photoelectric diode, it will light emitting the lights. That light is going to the gate to this device for the bias. Once the bias is there, then immediately it starts conducting. When it's conducting, then the signal will come over here. This is a triggering circuit. Then the triggering side will give the pulse to the SCR or this MOSFET or FET, this thing, and then it will conduct, and then the load will flow, and this is the protection. So input circuit is a small device where I can give the input voltage, but the input voltage is, suppose this is a 5 volt diode. So if the input voltage is 10 volt, then I cannot give this. So what do? We put a resistor where we can drop some voltage over here, so that ultimately 4 volt will come over here. And if it operate on the DC circuit, so in this change of polarity, to protect this input circuit from change of polarity, we put a reverse bias one diode. If the polarity gets changed, then it will not conduct. The light will go in the different direction. So it will protect this input circuit. That's why the reverse connecting diode, one diode is connected over here. So this is the input circuit where this resistance can be varied to give to change the input voltage or current input voltage. Otherwise, the input circuit can be also current drive. We can put a current generator who will give the current to this optodiode, this photoelectric diode to generate the light, which will go to the gate to this device, transistor. So this is a input device. Now, isolation circuit, I have already said, in the case of relay, we have seen the electromagnetic relay. There is a galvanic isolation we are giving between the magnet and the disc by giving no physical connection. So there is a automatically galvanic isolation is there. Here the isolation we put by optically. How we are doing this thing? This is a output. This is a transistor which is getting triggered or conducting when there is a signal on the gate. This is a photovoltaic transistor. So the gate or the base of this, it is a collector, emitter. This is a collector. This is a emitter, and this is a base. Suppose this is a normal transistor. So when the base get signal, this optical signal, the base get start conducting this signal, then immediately this transistor will start conducting, then the signal will come over here, okay. Then the signal will come, this is connected to the battery, then the signal will come over here and it will go to the trigger circuit. So this is actually the isolation, so this is isolation circuit. This photoelectric transistor is an isolation circuit. Now come to the triggering circuit. This triggering circuit, in the case of final output circuit, we use another transistor, either it's a FET or MOSFET, which need a base supply to start conducting, or it could be in the case of AC supply, AC load, we use the SCR or triode. Now, if we use SCR also has a gate, so it needs a anode, cathode, and gate needs a pulse to conduct the SCR. So, to create that pulse signal, there is a triggering circuit. There is a different type of triggering circuit. There is a resistor triggering circuit. There is a RC triggering circuit. Then there is a unijunction transistor triggering circuit. There are different type of triggering circuit is there. I am drawing one of the typical RC triggering circuit over here for just understanding how the triggering circuit work. Now, suppose this is a supply is coming from here, AC supply, okay, single phase AC supply. Then here we have a small resistor, variable resistor. Then we have a capacitor. It is called RC circuit. RC type, it is a RC triggering circuit. We call it, there is a resistance type, there are various type of there. Resistance triggering circuit. Then we have RC triggering circuit. Then we have third, we have UJT, unijunction transistor triggering circuit, which is the best one. Okay. Now, how RC triggering circuit works? Suppose this is a supply we are giving. Now, there is a diode over here. This diode, and there is a SCR. This is SCR. This is a gate. This is a gate. The gate is connected over here. And then there is a reverse connected. Now this is also connected in the forward way. Positive, this will be. This is a typical RC circuit. RC, how it is working? When the supply is there, immediately in the this is a positive. Suppose this is a supply. In the positive half cycle, what is happening? This is passing through this. This is a current is coming. This is a capacitor. This is a diode. So this is a positive in the first half cycle is positive. So diode is giving a power supply. The resistor is controlling how much current is required for this. In the negative cycle, what is happening? Then it become positive. The negative cycle, this become positive. This is negative. So this capacitor is getting fully charged through this. This capacitor current is flowing through this, and this through the diode it is getting charged in the negative cycle. Now, when the moment this in the positive cycle, when it start conducting, now in the negative cycle, this capacitor getting fully charged. So the moment this diode giving a signal to the SCR, this is SCR, immediately SCR giving the trigger signal, immediately SCR start conducting. Then this is a short circuited. Then immediately this capacitor will get discharged through this. Okay, so this way again in the next cycle it is repeating the same way. This way this signal is giving the triggering circuit over here, and it is protecting this diode. This thyristor also protected by this diode, so that in the negative cycle, when the cycle over here, it will not conduct, because in the negative cycle this diode is reverse bias, so it will not conduct. So it will be conducting through this. Okay, so this is the way it works. So this is a typical RC triggering circuit. There is the unijunction triggering circuit also there. There is a resistance triggering circuit is there. Nowadays circuit is coming in IC or PCB, a small version. So that is the triggering circuit for the SCR or this unijunction or this triac and all this. Now fourth is output circuit. What I said, that output circuit is a, for the DC we use the transistor FET or MOSFET. So there is also, this is a, suppose this is a transistor, and this is a gate signal, base signal is coming from the triggering circuit. This is a triggering circuit. It is giving triggering. Another point is that for the, now this is a triggering circuit. So when the circuit will go, immediately it will give conduct, and then there is a load over here connected. So this load is getting power supply. This is a DC supply. So normally when this transistor is not conduct, there is no current through this. The moment it start, when this signal trigger circuit come from here, immediately it starts conducting, current is flowing to this load. So this way, this relay, this up to this part, it is a relay part. So relay is conducting. In case of AC circuit, we cannot use this FET or MOSFET. We have to use the SCR. In the case of SCR, this is also same SCR. We have a anode, we have a cathode, and we have a base. So the triggering circuit will be giving a pulse. This type of pulse will be there. The pulse, or it could be different type of pulse. The pulse will be generated by this triggering circuit. When the pulse come over here, immediately this SCR will be conducting, and then this supply will be AC supply. Then immediately this will, suppose this is the motor is running, we want to start the motor. So the moment this triggering circuit come to the SCR, immediately SCR it will conduct through. This is a single phase, only half cycle it will work. If we want to use the full cycle, we have to use 2 SCR in opposite phase. That is this way it will work. And then it will go to the supply to the motor circuit. Power supply is coming from here, motor circuit. So this way reverse bias 2 SCR connected back to back for this single phase motor for the one phase. So this is actually triggering, and this part we call the output circuit. Now in the case of output circuit, these are the 4 devices. Input circuit, this is your isolation circuit up to isolation. Third is a triggering circuit. I said as one RC triggering circuit I have drawn. The 4 is your output circuit. Now fifth device is a protection device. What is this protection device? Now we'll discuss about the protection circuit. As we say, that is item number 5. We have already discussed, you see, in the case of SCR or triac, or in the output circuit, we draw the output circuit. This is a SCR. This is a gate, this is a anode, this is a cathode, and the load is connected over here. There is AC supply. Now this SCR, between the anode and cathode, what is the protection circuit? We have already shown one protection circuit in case of input circuit. In the input circuit, we have brought a reverse bias diode over here. That is a protection circuit for the opto-isolator. Now input circuit, I said this is a resistor. Now when there is a polarity, the supply is DC, due to the change of polarity, it should not damage. So when the polarity, immediately it will conduct through. So this diode acts as a protection device for the input circuit. Similarly, in the case of output circuit, there is a protection device required. Why required? This is suppose a SCR. In the case of SCR, this is anode, this is a gate, and this is a cathode. Here we are giving the triggering circuit. Now it has a 2 stages. One is a conducting stage, another is a non-conducting stage. Now this is a positive cycle, but this conducting stage depends on in this case, if this is positive, then only it will conduct. But the conduction will take place only when the gate signal is there. Suppose I apply the gate signal over here, then it will conduct over here, then immediately it will stop conducting, then go to non-conducting stage. But now what is happening, if there is with the time, if the voltage variation is too high, then there is another thing is happening in the non-conducting stage. This SCR can conduct. How that is possible? Now this SCR has a capacitance between the anode and gate. There is a capacitance between anode and gate, and this is the voltage we are applying over here. If there is a dB/dt, that is change of voltage with time, is very high, then what will happen? Due to the change of voltage very high, and due to this stray capacitance between the anode and gate, there will be current will be flowing that equal to C into dB/dt in the non-conducting stage. When it is non-conducting stage, when it should not conduct, due to this stray capacitance and due to high dB/dt, this dB/dt can come out due to switching operation, or can be changed due to change of voltage. This dB/dt can come, that can be in a steady stage or in a dynamic stage. If this dB/dt come high value, then immediately current will be flowing through in the gate and anode, and which cause the trigger of this gate signal, and the anode will conducting in the non-conducting stage when it should not conduct. Then the load will be burned out. So to avoid this undesired situation, what we do? We put an RC filter over here. This is resistance, this is capacitance, this is RC filter circuit. Now when this has happened, when there is a high dB/dt, what is happening? Immediately this high dB/dt, the tangent will pass through this. This is a pass filter. Through this low pass filter, immediately this high dB/dt will pass through this, and it will not come to the SCR or triac. Then the SCR will be protected. This way, this is called protection device. This RC circuit also called snubber circuit. This is also called a snubber circuit. So this dB/dt, if the dB/dt, normally dB/dt can withstand by, so if the dB/dt is very high, then we have to use this snubber circuit, and steady state dB/dt, if it is 500 volt per microsecond, in the dynamic state it goes to 10 times 1/10 of that value. So dynamic state is more sensitive to this dB/dt operation. Therefore, in this SCR, in this output circuit, always you use a RC filter, which will be a low pass filter, then it will high pass filter. It is a RC filter that will eliminate this dB/dt issue. So this is called the protection circuit for the case of solid state relay. So this is all about today. And then now from this we can make out the solid state relay has a various advantage. This advantage is a small in configuration, it is a small in physical size, it has a high switching speed, and it does not corrosion immunity is very high. Then it has a high life also. In the long life is long. Cost wise, in the long run, if you calculate the cost will be lower. So these are the various advantages of the SSR relay over the electromagnetic relay that we will discuss on this digital numerical relays over. Then we will compare all the three relay with their merit and dismerit, and we will discuss this thing. So this is all about this too. Now we will close this session today. Up to this, the next session we will consider. We will go ahead further to give about the digital numerical relay and the various comparison of the various types of relay. Thank you very much for joining with this session, and thank you very much for your time and energy. And it will be highly appreciated if you convey your comments, observation, your advice, suggestion to improve it further. That will be well appreciated. Thank you very much.